And Marta, the floor is yours.
Thank you. So first of all, thank you to the organizers for inviting me 2 years ago. I never thought I would make it to Marrakesh, and it's great being here. I'm really sorry I couldn't come here earlier, and I missed the conference actually, and even the beautiful banquet, but better late than never. And I hope I can interest you a bit for the radar world today, and explain a bit what we are doing now at Renesas, and what are the challenges that we are facing. So as a background, I moved to Renesas about 16 months ago, and I didn't know anything about semiconductors. Renesas is has 1/3 of the market of the semiconductors for microcontrollers in the car industry. So what does it have to do with my previous life as an antenna designer? Very little. But we are moving into the radar domain. So radar for automotive requires a large insight in what happens from the electromagnetic point of view. That's why I moved to this company, and I'm trying to convince them that electromagnetic simulation is a very important aspect of the design, also in the semiconductor industry. So let's see what is the problem. So why are we using radar? Well, I don't know if you drive. I guess most of you do, but you should know that more than 9 in 10 accidents are caused by human errors. So if we can remove the human aspect from driving, and you feel comfortable with a car driving for you, we can remove most accidents on the roads. That's why there's the so-called Vision Zero. That means, at least in Europe, but also in many parts of the world, that we want to achieve 0 deaths in the traffic by 2050. So it's a very ambitious target. And in a shorter time, we want to have a 50% reduction of all accidents by 2030. And how we do that? We make our cars more secure. We make our cars more independent from the human being. How do we achieve that? By integrating not only radar, but line change detection systems, emergency brake. For example, emergency brake systems are compulsory in all the cars, the new designs of cars in the European Union, starting this month. And it will have to be in all sold cars in 2 years' time. So we force people to adopt these security measures. But of course, forcing people is not always the best way. So what we do is also to have it in the new car assessment program. That means all the cars are tested and they get some stars. But of course, when you are buying a car, you are doing an investment, you go there and you want to have a very good car. People want to have the best of it. So you look how many stars it has. Stars can be given for comfort, how well it drives, how nice it looks, but also we include some security assessments there. And the test regarding this autonomy will also be included, so that we will buy the cars just because they are better. Anyway, I will talk today only about radar. And where do we find radar? At the moment, not everywhere. No, at the moment, we find it only mainly for adaptive cruise control. But we want to increase the number of radars to create what we call the cocoon around the car, the 360-degree panorama of what happens around. And for that, we have to integrate long-range sensing, mid-range sensing, and short-range. Of course, the radars will be different, but they will also operate all in the same frequency bands because they are the ones allocated by the regulation. What we want to achieve is to go from what we have now. So level 0 of autonomy is very old cars, the old timers, you cannot control anything. We are now about here at the level 2 that we call fit off. That means if you are in a motorway, your car will automatically accelerate or reduce the speed according to the distance with the car in front of you, and even brake if there's a threat ahead. In the next couple of years, we will move to level 3+, 2+, and even 3. That means hands off. I don't know if you have a car with a lane change assistance that when you go over the line without blinking, it tries to steer you back. So you could just let your hands off. But in the future, it's going to be more. So the car will take its own decisions. And level 3 and 4, that's for premium cars. It's what we call eyes off. The car will drive itself. You will have to sit there at the steering wheel just for, let's say, insurance reasons and for regulatory reasons. But the car is able to take the decisions and drive itself. Level 5, the so-called minds off, is when the car does everything. It doesn't need to have a steering wheel. This scenario will be very limited. It's, for example, for robotaxi and closed environments, because that will be mostly because you will never get a law approved to have these cars at the moment in the streets. And no insurance company will take care of that. There are ethical issues, etc. But as you see, to implement this, we will have to increase the number of radars that we have on the car. We're also moving from the first radar systems for the cruise control were in the 24 gigahertz band, which is ISM band. The problem is it causes interference, for example, to radio astronomy. So we have moved now to 2 other bands, 76 to 77 gigahertz. That's for cruise control, for example. It's what we call for comfort. So you are driving in the motorway and you don't have to think about the fact that there may be a traffic jam in front of you and you have to brake. Or when you are just driving, it keeps the distance, it keeps the speed. That's perfect. So for that, we have 1 gigahertz bandwidth. And we will have a second category that is for improved safety, 4 gigahertz bandwidth, that is for shorter range, but we want also to extend it to the high range. And it is to have a higher resolution, because increasing the bandwidth gives us more resolution in the range. And that will be for all other applications, from parking assistance to replace the ultrasound. We can detect pedestrians and bicycles at low speed, so to have more security around the car. Or we can use it for imaging, to have a very accurate description of the surroundings with azimuth and elevation. Of course, there's a benefit of moving to 70 gigahertz is that the antennas will diminish in size dramatically. So you see here a comparison. We can integrate them much easier, more easily. Of course, there's another problem here. Moving up in frequency, and you all know that, makes it much more difficult to design them, must make them more susceptible for tolerances in the manufacturing and in the materials. So I will skip this one because I'm quite late. So here is the typical radar. So very easy. We will have what we are designing is the radar transceiver that has all the transmit and receive chains. In our case, it also performs the first FFT to determine the range. But we will need a microcontroller or a system on chip to determine the runtime, to determine everything, and to do the processing. And of course, we will need some other things, regulators, power microcontrollers, and some timing devices. So all that has to be integrated in the radar front. The question is, what is to be done in this radar front? So there are some things that are very clear. We have to transmit the signal, put it in the right frequency with the right waveform, and send it. And then we will receive on the other side. And when we get it back, so we will have first an analog front end, so typical low noise amplifier, mixer, and then some signal conditioning, so the filtering, so that we have a nice signal that then we can convert into a digital signal. And then we perform all the radar process. So the people from the digital part say that's the most important, but if we don't get the received signal right and clean enough, the rest is not going to help us. The question is, where are we performing all these operations? Of course, it is clear that the analog part will take place in the radar MMIC, in the transceiver. But where do we do the range FFT, the Doppler to determine the velocity, and all the MIMO and advanced processing to determine the direction of arrival will depend on the geometry and the topology of our radar. And of course, there are some operations that will take place in the central processing unit of the car. So as you can see here, the technology is exploding. So we are getting more and more radars, and the trend is to move away from gallium arsenide, which was the first choice in the 2010s because of the power. We moved to silicium germanium and silicon germanium, and it's going to stay for a while. But of course, now the trend is moving to CMOS because it allows us to lower the cost, and it allows us to integrate the full RF front end, but also all the digital parts in the same die. And that will make it much more powerful from the processing point of view. And we also lower the power consumption, which is quite important because power consumption means heat, and the radar processing will take place in very hot environments. So we want to avoid heat at any cost. That's what it looks like. So we have the transmit front end and the receive front end. We have the signal generation. For transmit and receive, we want to have maybe some phase shifters included so that we can perform a shaping of the beam and direct it in some directions. Or we want to have analog beamforming in which we combine several transmitters, several receivers. And of course, we have to output the data using high capacity interfaces because we have, for example, a certain number of transmit channels and receive channels. That means that we generate a very high data rate. And we will need for that, for example, VPCSI interfaces or Ethernet, gigabit Ethernet interfaces in some cases. But let's go to the part that interests more the people that are into high frequencies. What is that the influence on the performance? So the first aspect that we have to consider is the transmitted power. And for that, we have to go to the radar equation and take a look and separate the different parts. The radar equation will link the received powers, of course, to the transmitted power, the antenna gain, and the characteristics of the channel and the target. We cannot control the target, we cannot control the channel, we only can control the antennas and the transmitted power. As a semiconductor person now, I can only control the transmitted power. And for that, I have to maximize it. How do I maximize it? Well, I have to make a good design, not only of the power amplifiers, but also of all the transitions to the board and to the antenna. And ideally, co-design the antenna, the transition, and the chip. And that's where we're at now. Take into account that we are working in a very bad environment. Already, if you integrate the cars behind the radar behind the bumper of the car, you can have up to 8 dB signal loss just due to the integration. So we have a lot of losses. So every dB will count. Just an example, I took some reference antennas from Etsy, and I did a very simple calculation with a sensitivity, so a minimum received powers of 110 dBm. Just increasing 1 dB the transmitted power will give me 2.8 more meters to detect a bike in the long range. That means that I could avoid more easily an accident. And the same for the car. I can win up to 11 meters to stop at the end of a traffic jam on the motorway. And that's very important in Germany, where I live, because there's no speed limit on the motorway. So, and traffic jams are very usual. So that's the important thing. So the challenge here for simulation is optimizing the interfaces so that I don't lose a single cent of dB. So I want to get everything. Then we have the problem of the antennas. So here, very easy antenna, just one transmit array and 4 receive arrays. And I place the antennas in a way that I get the maximum field of view. That means that every column has to be about a half of a wavelength apart. If you make the math, that means that for the frequencies we are operating around 80 gigahertz, the separation between 2 receive arrays will be about 2 millimeters. And the size of each patch is under 2 millimeters. So very tiny, and we have to be very accurate. So, of course, what we want to have is to have a very equal conditions in all the transmit and all the receive antennas. So we have to design the antennas in a way that even with the coupling, we get a radiation pattern that is as equal as possible to the neighbors. And sometimes what we want to do is to add some parasitic elements outside, otherwise the array elements outside will be different. So we compensate it by adding some dummy antennas, we call them. So we want to have this in elevation and azimuth. So you see here, we have the two external arrays are identical and the two internal are identical. But there's a difference here about, well, I don't have here, so it's about 1 dB, I would say. And this we compensate, as I mentioned, adding some dummies. But the amplitude is not the main, it's very important, but not the main parameter. What we want to have also is the capacity of distinguishing between two directions of arrival. And for that, we have to look at the phase. So if we have a distance about half a wavelength, we will have the maximum field of view. That means that we can distinguish directions of arrival from -90 to +90 degrees. That gives us a very wide angle for this, but the resolution, as the slope is very slow, it increases slowly, the angular resolution will be low. We need for that to have antennas that are further apart. That means that we have a steeper slope, more angular resolution, but then we have a smaller field of view. By having several different receive antennas, we combine the advantages of distance, of a large field of view and steep slope. So at the moment, we are working with 4 receive antennas, and we are adding 4 transmit antennas. So in total, we get 16 different channels for which we can determine the direction of arrival. So we get very high accuracy. Of course, that's nice and dandy for the theory, but in practice, we have to take into account the mutual coupling. So there's our simulation results, the mutual coupling between the antennas. And that's only the patches. I didn't include the lines. And here you already see that the field of view is already reduced due to the coupling. And also the slope is not so nice. If we add additional effects like components on the board, if we add the transmission lines that we couple, the field of view will be even reduced in a more significant way. I mentioned that we have 4 transmit and 4 receive antennas. Why do we do that? It's because we want to do MIMO. So, for example, instead of having 1 transmit antennas and 8 receive antennas, what we can do is have 2 transmit antennas placed 4 times the distance, and then only 2 transmit and 4 receive. And we will have exactly the same number of channels and exactly the same characteristics of the channels. So that's what we all know as MIMO. And we can create a virtual array that occupies less place on the PCB and in the car, and makes it easier to implement. Of course, we shift the problem to the signal processing people, which is not bad because they have to work on something. In the future, if we want to have higher resolution, what we will need is a much larger number of channels. So we talked recently to some car manufacturers. Having these 64 channels that we have here in this imaging example, sorry, not 64, there's a mistake there, is 256 channels. That's not enough for them. They want to have 1,000 channels, and even better, they would like to have 2,000 channels. So they will need to cascade a lot of single MMICs and combine them with one single processing unit so that they get a giant number of channels, or we have to design larger MMICs with a lot of transmission or a lot of receive channels, or 2 separate MMICs, 1 for transmit and 1 for receive. So we have the choice. What are we going to do? Well, it will depend, because here with this configuration, we have more flexibility. For a semiconductor manufacturer, it's better to have this because I do a part and then I just cascade it and I sell a lot of parts. But this configuration is more focused for a specific application. And that's the way that some startups like Mobileye, Under, and similars are going. They make very large chips. If you look at the problem for antennas, here you will have very complex routing to bring the signals to the antennas. Imagine you have 16 or 32 or 64 antennas that have to be connected to a chip. You will have to see how to put it and how to route everything. And you have some thermal problems also. Of course, here we have other problems. Here, it's easier to place the antenna. It's easier from a thermal point of view, but we have the problem of synchronization of all the different chips. So what's better? It will depend on the applications. But what will be always the challenge is to simulate the full antenna aperture, because now we are talking about this size that we can discretize, but if we are going to this size, it will take a lot of memory, it will take a lot of time and computing capability. So big challenge coming ahead. If we stay with the antennas, I mentioned that going up in frequency will also affect the tolerances. What happens if you just change the substrate? So I'm working in a company, as I mentioned before, in which the experience lies in the digital domain, microcontrollers. So when they decided to make a test board for this, they just received the layout from a third party that had made a board for the testing. And they went to their usual manufacturer, and the manufacturer said, well, yes, we can do it, but we don't have this material. But we have this other one, which is almost the same. So they changed from Astra MT77 to Rogers 3003, or the other way around, I cannot remember. Looked nice. It's just a change from Epsilon R3 to Epsilon R3.1, nothing. But you see, we had directly a big mismatch at the frequency operation. We lose directly, for some of the antennas, about 60 dB gain in the direction of interest. And we have a complete deformation of the radiation pattern. Why? Because no one had considered making a simulation to see what happens, because they didn't have the know-how about that. They didn't, of course, they didn't know about it. They were no experts in the company at the time. That's why I got a job. Well, no, it was not because of that, but I found this and I decided to make it my job, to train them. Anyway, so you see, it's very important to take those things into account. Also, within the same material, there may be variations. So what I would always recommend is to make your test boards and then characterize the substrate according to your needs, because of course, manufacturers of substrates only make the assessment for quality reasons and at certain frequencies. And it may not be the frequency you are working at. So always do a test board, characterize the substrate before you go ahead. We have another problem, is that, yes, we do our very nice radar transceiver, we design a very nice antenna, and then someone comes and puts a radome on top of it, makes a casing, and they say, well, it's a casing, it's plastic, who cares? Well, I do, because as you can see here, putting the radome on top of that may degrade the radiation patterns in a very destructive way. Here, we almost had a null in the radiation direction of interest. So with no radome, we have a nice radiation. I add a radome with a permittivity of 2. It starts creating some standing waves here, some reflections. If the permittivity goes to 3 or 4, which is quite normal for plastic materials that are put on top of the antenna, you see that the radiation is completely destroyed. So we have a lot of reflections that we have to take into account in the design phase. So the radome has to be co-designed with the antenna, or the antenna has to be co-designed with the radome. And that's for a fixed distance. If we add a second variable, which is changing the distance between the radome and the board, and it's not much, it may be due to tolerances, we again have an increased effect. So electromagnetic simulation is quite challenging because first you have to convince people that they need to do it. And secondly, because it takes a lot of time and a lot of experience to get it right. That's good news for electromagnetic simulation people, because we cannot be replaced so quickly. Third aspect that I want to consider is detecting, for example, EMC problems. So here you can see if we have the board and the antenna, we have a near field distribution that looks quite nice. But then they did some measurements. So they manufactured the board, they did some measurements and they said, whoops, there are some problems here. We have some interference, we have coupling. What happened? Well, they had put some RF shields on top of the chip to avoid interference. What they created were some resonances inside this RF shield that degraded the performance. And you see that we get some interference going into one of the digital channels. So we also have to take care of electromagnetic simulation of the whole board at the end stage to see that we avoid these problems. Here it was easy. We said, okay, just take off the RF shield and it's going to be okay. But in other cases, that may be a big, big problem. So as a conclusion, and I think I was quite quick today, sorry, radar is now a feature that has come and it's going to stay. And we have a system that has a higher reliability against adverse weather. I think here in Marrakesh it's not a problem, but in the Northern Europe, rain and fog are a big problem, and for cameras and for LiDAR. So radar is very reliable in these conditions. We have also the advantage that semiconductor industry has been advanced a lot in the last years, so that we can get cheaper components and more reliable. But still, and that's what they have to learn, is that electromagnetic simulation is going to be capital for a good performance. Because we want to transmit the power in an optimum way to the antennas. So that's the case for transmit, but the same applies for the receive channel. So we want to get as much power from the air as possible. And so we want to optimize the interfaces, and we want to optimize the overall system performance, taking into account, in our case, not only the transceiver itself, but the board, the antennas, the radomes, and even how we integrate it behind the bumpers or in the whole car. That will be very important, and that's a challenge for the simulation. So thank you for your attention.